Our story begins not with a bang, but with a vast, swirling cloud of cosmic gas and dust. This immense structure, known as the Solar Nebula, was the primordial soup from which our entire solar system would eventually emerge. It was a truly colossal entity, stretching light years across the emptiness of space. The composition of this nebula was quite remarkable. It consisted primarily of hydrogen and helium, the lightest elements forged in the crucible of the Big Bang itself. These fundamental building blocks made up the vast majority of the cloud's mass. However, the nebula also contained a crucial ingredient: heavier elements. These elements, like carbon, oxygen, iron, and silicon, were not created in the Big Bang. They were forged much later, deep within the hearts of ancient, dying stars that had lived and died long before our sun was even a flicker. When these massive stars reached the end of their lives, they exploded in spectacular supernovae, scattering their enriched material across the galaxy. Our solar nebula was one such recipient of this cosmic legacy, inheriting the raw materials necessary for planets, moons, and even life itself. For eons, the solar nebula drifted, a quiescent giant in the galactic arm. But its peaceful existence was destined to be disturbed by a cataclysmic event. The most widely accepted theory points to a nearby supernova explosion as the catalyst. This wasn't just any explosion, it was a cosmic shockwave. The immense energy released by the dying star sent a powerful ripple through space, impacting our relatively stable nebula. This shockwave acted like a cosmic nudge, compressing parts of the cloud. This compression was the critical trigger. It increased the density in certain regions of the nebula, causing the force of gravity to become dominant. This subtle yet profound disturbance initiated the nebula's inevitable gravitational collapse. Without this external push, our solar system might never have formed. The supernova, a destructive force elsewhere, was a creative force for us, setting in motion the chain of events that led to our existence. Once triggered, the nebula began to contract under its own immense gravity. As particles were drawn closer together, the cloud started to shrink. This contraction had a profound effect on its rotation. Think of a figure skater pulling their arms in during a spin. As their mass concentrates closer to their axis of rotation, their spin speed dramatically increases. The same principle applied to our collapsing nebula. As the nebula contracted, its rotation accelerated, causing it to flatten out. This flattening was a natural consequence of the centrifugal forces at play. The once amorphous cloud began to take on a distinct shape. The outcome of this process was the formation of a swirling, pancake-like structure known as a protoplanetary disk. This disk, with a dense bulge at its center, was the birthplace of our sun and all its orbiting companions. Within this newly formed protoplanetary disk, the vast majority of the material gravitated towards the center. This central region became incredibly dense and hot due to the relentless force of gravitational compression. It was here that our sun would be born. As more and more gas and dust accumulated, the pressure and temperature at the core of this central mass soared to unimaginable levels. The conditions became extreme, far beyond anything we experience on Earth. Eventually, the temperature and pressure reached a critical threshold. At this point, nuclear fusion began. Hydrogen atoms, under immense pressure, fused together to form helium, releasing an enormous amount of energy in the process. This ignition marked the birth of our sun, a true star. It began to shine brightly, radiating light and heat, forever changing the environment of the surrounding protoplanetary disk. Our solar system now had its central powerhouse. With the sun now blazing at the center, the remaining material in the swirling disk continued its own evolutionary journey. This material, still orbiting the young star, was destined to form the planets. The process began with tiny dust grains, microscopic particles floating within the disk. These grains started to collide with each other, not just bouncing off, but actually sticking together. This initial clumping was driven by electrostatic forces, similar to how static electricity makes dust cling to surfaces. As these tiny clumps grew, they became larger particles. This process of gradual accumulation, where smaller particles combine to form larger ones, is known as accretion. It was a slow but relentless building process. Over time, these growing particles continued to collide and merge. They eventually reached sizes of several kilometers across. These kilometer-sized objects, the true building blocks of planets, are known as planetesimals. The protoplanetary disk was not uniform. Conditions varied significantly depending on the distance from the young sun. In the inner, hotter part of the disk, closer to the blazing star, temperatures were extremely high. These intense temperatures meant that volatile substances, like water ice, methane, and ammonia, could not condense into solid form. they remained gaseous, unable to contribute to the formation of solid bodies. Consequently, the planetesimals forming in this inner region were composed primarily of rocky materials and metals. These substances have high melting points and could solidify even in the intense heat. They were dense and resilient. These rocky and metallic planetesimals continued their violent dance, colliding and merging over millions of years. Each impact added mass, gradually building up larger and larger bodies. This process was often chaotic, involving massive impacts. Eventually, through countless collisions and mergers, these growing bodies coalesced into the 4 inner planets we know today: Mercury, Venus, Earth, and Mars. These are our terrestrial or rocky worlds. Beyond the inner solar system lay a crucial boundary known as the frost line. This was the point in the protoplanetary disk where temperatures dropped significantly, becoming cold enough for ice to form. Beyond this frost line, water, methane, and ammonia could condense into solid ice. This meant that the planetesimals forming in the outer regions had access to a much greater abundance of solid material. They incorporated significant amounts of ice in addition to rock and metal. With this extra icy material, these outer planetesimals grew much larger and much faster than their inner counterparts. Their increased mass gave them a stronger gravitational pull, allowing them to attract even more material. As they grew, their gravity became powerful enough to capture vast quantities of hydrogen and helium gas from the surrounding nebula. This gas accretion was a runaway process, leading to enormous growth. This rapid accumulation of gas and ice led to the formation of the gas giants, Jupiter and Saturn. Further out, where material density was lower, Uranus and Neptune formed more slowly, accumulating more ice than gas, earning them the title of ice giants. Once the planets had largely formed, the solar system was still a messy place, filled with leftover gas and dust. The young sun, however, had a powerful mechanism to clear this remaining debris. The sun began to emit a strong stream of charged particles, known as the solar wind. This early solar wind was far more intense than what we experience today, acting like a cosmic broom. This powerful solar wind swept away the remaining gas and dust from the protoplanetary disk. It pushed these lighter materials out into interstellar space, effectively cleaning up the solar system. This clearing action had a crucial effect. It halted the planet-building process. With the raw materials gone, the planets could no longer grow by accreting gas and dust, solidifying their final sizes. Even after the solar wind cleared most of the debris, not everything was swept away. Some smaller remnants of the original protoplanetary disk remained, providing clues to our solar system's early history. These leftover objects include the asteroids, primarily found in the asteroid belt between Mars and Jupiter. They are rocky and metallic fragments that never quite coalesced into a full-sized planet. Further out, beyond the orbit of Neptune, lie the comets and Kuiper Belt objects. These icy bodies are pristine remnants from the outer, colder regions of the original nebula, preserved in a deep freeze. These cosmic fossils offer invaluable insights into the conditions and composition of the early solar system, providing a window into its tumultuous formation. The formation of our solar system was not an instantaneous event, but a gradual process spanning a significant cosmic timescale. From the initial collapse of the nebula to the clearing of debris, it took millions of years. Estimates suggest this entire process, from cloud to fully formed planets, occurred over a period of a few million to tens of millions of years. This might seem long, but in astronomical terms, it was a relatively swift transformation. The result of this incredible cosmic journey is the diverse and fascinating solar system we inhabit today. A system born from dust and gas, shaped by gravity and stellar forces, and teeming with worlds waiting to be explored.